Welcome. In this section, we are going to explore the radiation protection paradigm, which means the set of science, assumption, and values which make radiation protection today. This is quite a general chapter, but the basic principles of radiation protection will be explored and explained. Reference to this section are, of course, the recommendations of the International Commission of Radiological Protection, and namely, as you will see later, the recommendation 103. The content of this lecture is indeed presented in several chapters, but specifically in Chapter 5 and in Chapter 6 of the recommendations, and in the Annex A, which is exploring the biological and epidemiological information related to health risks due to radiation. If you are using the textbook Atoms, Radiation and Radiation Protection, some of the information that we are going to discuss in this chapter is presented in the Chapter 14. The Chapter 14 is called Radiation Protection Criteria and Exposure Limits, and it is a presentation of both the NCRP, the National Commission on Radiological Protection in the United States, and the ICRP concepts. Due to the fact that the book was prepared for the United States reader and therefore has the point of view of that country in terms of legislation and recommendations. Some of the concepts which are presented in that chapter in the book are not automatically applicable in the UAE. The UAE have adopted the ICRP, the international system, as it is reported in the IAEA Basic Safety Standards. In this section, we are going to describe the radiation protection paradigm. The paradigm I am referring to here is the series of assumptions, the series of ideas, the scientific content, and the hypotheses which build up the system of radiation protection as it is understood today. You don't have to think that radiation protection is a science which has been completed, which is known in every aspect. Well, first of all, radiation protection is not only science. It is more than that. There are considerations which go out of science. And this makes radiation protection judgment tricky sometimes. Because when you can measure and you can quantify things, as we have seen in the dose quantity section, it is easy to compare. But if you cannot quantify societal value or ethical values, how can you make a decision? You will see that radiation protection in the recent years has been working also on those topics which are not scientific in nature, but they have an important impact on this discipline. Specifically, in this presentation, I am going to present the structure of the ICRP Radiation Protection System. Now, the ICRP is the most important institution in radiological protection. It is called, first of all, ICRP because it's the acronym of International Commission on Radiological Protection, ICRP. This institution has been formed in the late 20s, in 1928, although the work on radiological protection has started, of course, immediately after the radiation was discovered. Indeed, just a few years after the discovery, the first diseases connected to radiation exposure were highlighted, and the very first rough recommendations on radiation protection were issued much before 1928. However, the foundation of this organization is formally recorded in that date, which is, as you can see, almost 100 years ago. Now, what happened in these 100 years? Many advances in understanding how radiation is impacting health and what are the consequences of radiation exposure to our well-being. And all these science and these conclusions have been distilled into publications. Now, today we are around 140 publications in 2020, and these publications are all available on the ICRP website. Most of them, thanks to the effort of many organizations and first of all to FANAR, have been made freely available to the public, which was not the case, for example, when I studied. When I started in this profession and when I was in university, the ICRP publications were all paying, so I had to go to the public library, to the university library, to consult them. And it was, of course, not possible to photocopy them. The advantage you have, you just go to the icrp.net website or .org website, and you will find all the publications there, freely available for your download, with the exclusion of just a handful. The latest ones, I think the last 2 years, are not freely available, but they will become available when the 2 years have expired, and they can be bought for a small fee. Now, this is not to advertise the ICRP, but to stress the importance of this institution, with which FANAR has an agreement since many years now, and there is an ongoing collaboration. So you have access directly to the most important radiation protection institution in the world. Now, the work of the ICRP is not to make science, but to collect it, discuss it, and distill it into technical documents, and in some cases into more general technical documents, which represent the broad knowledge in radiation protection, and they are called recommendations. Now, the recommendations are a sort of compendium of all the knowledge in radiological protection in a specific time. The latest recommendations were issued in 2007 in the publication 103. These recommendations are freely available, thanks to FANAR, for the whole world, and you can download them freely, and you can see in that publication the foundations and the very latest research in this discipline. I highly recommend to download that document and read it, because it's really enlightening in radiation protection. There have been additional recommendations previously to that, the famous 1990 recommendations, the publication 60, the publication in 1977, recommendation 26, and others in the past. It's historically interesting to see how recommendations have evolved in time, but for us, for the discipline and to use the latest science and the latest approach in radiation protection, we need to consult and use the latest recommendations. So, recommendations contained into the publication 103. The system of protection from radiation is based on a few pillars. It's made basically of reference anatomical models of humans. We are going to discuss a bit later what this means, but I hope this can give you already an idea of what reference anatomical models are and why they are important. Radiation protection is not a science which is based on an individual. It's based on a reference person, and this reference person is the person on which calculations are done in order to obtain what we have defined: equivalent doses and effective doses, and coefficients which relate exposure to radiation to doses in individuals. To this purpose, specific models have been developed for the human beings. Of course, studies are the most important content for a scientific discipline, so studies at the molecular level and at the cellular level describing the impact of radiation and its consequence on the cell and on the moleculae of the cell are of utmost importance. And of course, it's not only understanding what happens when radiation is impacting on cells and molecules, but it's also studying how the entire organism is reacting to that. And here, as you can imagine, there is a high variability. Experimental animal studies have been performed in the past, and in a way, they are performed also today, although there are ethical considerations. And another important component are the epidemiological studies. Epidemiological studies are studies which are performed on big populations of humans in order to verify if there is a different impact of radiation exposure into specific conditions related to health of people in the world. So now let's have a look now at the different components. This will not be a technical discussion, but will provide you, I hope, elements to understand how the radiation protection system is composed, and later also to see what are the principles on which and assumptions on which radiation protection is based today. We need reference models in order to calculate conversion factors which allow to transform quantities in the radiation field into those quantities that we cannot measure. To be clear, we can measure the characteristic of a field, but we cannot measure the equivalent dose or the effective dose. So how do we obtain those? Well, as you will see later in the presentation on the external exposure and the internal exposure, we imagine that the reference person, computational model of a person, is introduced into that field, and computer calculations are made in order to calculate what are the equivalent doses to all the organs, and then to calculate what is the effective dose. And going backwards from those equivalent doses and those effective doses, scientists calculate conversion factors going, as you can see here, from unit intake of radioactivity to committed dose, which is a measure of effective dose due to the intakes of radionuclides. We will see that definition later. But for what you already know, from kerma or fluence for external exposure, going to equivalent dose and effective dose. These reference anatomical models are very important because they allow the determination of coefficients for the exposure of workers, the public, and patients, of course, and specifically in the category of the public, of those elements of the public who are more at risk. Infants, babies, children at various ages, pregnant women, the embryo. You will see there is a lot of effort in this regard. An interesting aspect, I would say an interesting engineering aspect in all this, has been the development of computational phantoms. Phantoms had been introduced already many years ago, especially for medical radiation protection calculations. But in the recent years, those models have reached a level of complexity and perfection which is amazing. It's really very, very impressive. Now, these models today, they are called reference male and reference female models. They are based on actual computational tomography images, which are then being adapted to the specific characteristic of the reference person, which is defined by the ICRP, with specific masses of the organs and specific sizes. But these models are very, very advanced, and they are very realistic because they are based on chopping down the body into voxels. Voxels are pixels for the 3D. You know that images on a cell phone are made of pixels, of points, okay? So if you want to make a model which is a 3D model, what you will use will be pixels in 3D. Now, these elements are called voxels. I also want to add that a recent endeavor that the ICRP is developing, together mainly with partner universities in Asia, has been the development of even more advanced models based on so-called NURBS, which are polygon mesh-type models, very, very advanced and able to change the size of what are here the voxels in those type of models are mesh polygons. The finesse of the mesh is varying depending on the specific tissue, because in some cases you need more finesse, There are maybe layers of tissues which are at the microscopic level. And in other cases, you don't need such a finesse because maybe that tissue or that organ just requires a larger mesh of definition. There are huge efforts, and this is very interesting and passionating, I would say, because it's a very recent development in radiological protection, and there are a lot of efforts there. Epidemiological and experimental studies. Of course, in order to express risks in population of humans, we need to be able to define which are the effects of radiation exposure of populations. So we need basically to have informations related to the real population which are exposed to radiation, and this is done by performing so-called epidemiological studies. Epidemiological studies are studies of larger populations which are aimed at developing so-called risk factors specifically due to a kind of exposure. So, for example, epidemiological studies are done in the chemical field or in the medical field to express relationship, a risk factor between use of cigarettes and cancer to the lungs, or to exposure to specific chemicals like exposure to asbestos, to specific risks in the case of asbestos, again, a very special kind of lung cancer. Not only epidemiological studies are done, so studies on larger populations, but also biological studies on organisms. Now, these biological studies, as you can imagine, are done on laboratory animals, which can be mice, they have been dogs in the past, and in some cases, even on human populations, many years ago when populations were exposed by the effect of accidents, for example, or maybe by the effect of a mistake in a medical procedure, or maybe during testing of atomic bombs in the 50s, in the 60s. So those conditions, which were very specific in the past and cannot be replicated today anymore for ethical considerations, they are also a basis which provide data, important data, to complement the animal studies. And specifically, for what concerns cancer, which is one of the most important outcomes, you all know that radiation has the ability to generate cancer in humans. So this is a very relevant outcome, result of irradiation or exposure to radiation, which has to be studied specifically with attention and care. But some of you also know that radiation can generate effects which could be transmitted from one population to another, the so-called heritable effects. Studies have been performed on cancer and heritable effects as well to evaluate the effect on human and animal genetics. Now, the current ICRP Radiation Protection System, which is the international system because every country in the world adopts a radiation protection system which is related, if not exactly the same, as the one which is presented by the ICRP. Why? Because this is the result of a collaborative effort of hundreds of scientists and experts for so many years. So there are specific details which may vary from one country to another, but in its essence, in the gist, the radiation protection system is the same everywhere in the world. And this system is based on a series of components that we are going to analyze here one by one and discuss them also. One important element is a characterization of the situations where radiation exposure can happen. It can happen in situations which are already pre-planned in advance, or it can happen during an emergency, which is not necessarily known in advance, or it can happen in conditions which are called existing exposure, result of past activities, or result of a condition which is pre-existing, like radon in homes or cosmic exposure, cosmic radiation exposure. The ICRP defines today 3 exposure situations. They are called planned exposure. And as I said, these are exposure which are known in advance. The operation of a medical cabinet, the use of radiotherapy, nuclear power plant, a laboratory for the preparation of radiopharmaceuticals. All these are situations in which it is known in advance that radiation is going to be used, and it can be assessed in advance. Existing exposure situations in which exposure is due to past practices or to exposure in the environment due to natural radiation sources or similar cases, and emergency exposure situations in which the exposure is due to the fact that the source is no more under control for a situation which has not been foreseen before. It has been foreseen, but it was not known that it will happen at that specific time. Incidents, accidents, they can all lead to emergency exposure situations. Another characterization is the type of exposure. There are some exposures which are certain to occur, like exposure in a workplace or some existing exposure situations. Others which are not for granted, they are not certain, so they are potential. They may come from an emergency situation, or they may come from a medical practice if a person is subject to a medical practice. Otherwise, they don't happen. And in line with this, an identification of the exposed individuals. Of course, we have workers. Some people are exposed to radiation due to their profession, medical practitioners, or radiation workers in a nuclear power plant, or NDT workers operating a high-activity source to monitor, for example, welding in an industrial construction site. But there are also patients which are exposed in order to obtain diagnostic information or for cure, for therapeutic purposes. And there are also the members of the public who don't necessarily have any benefit in the exposure to radiation, but they should be, of course, considered and they should be protected from radiation. Therefore, three kinds of exposure are defined. There is exposure related to work, which is called occupational exposure. And for example, you, as inspectors at FANAR, you are occupationally exposed to radiation. Some of you may also be exposed to radiation for medical purposes, if you need to have a specific exam. And all of us, including you as inspectors, you are subject to existing exposure situations, to cosmic rays, to radon in whenever we are staying at home, at work, wherever we are going for other purposes, we are exposed to cosmic rays, radon, and irradiation from the Earth. So, occupational exposure refers to workplace-related exposure. Public exposure means exposure of the general public due to a variety of sources, artificial and natural. And medical exposure, meaning of patients, because doctors and nurses and other personnel are already covered into the occupational exposure framework. Medical exposure of patients is the exposure of people who are subject to radiation in order to obtain an advantage in terms of diagnostic information. Radiation can provide specific information that other techniques they cannot provide, and for the benefit which comes from therapy, in the case of radiotherapy. So these are the categories of exposure to radiation. Another important element is the type of radiation assessment, which can be either source-related, so the assessment of the risks may be done for a specific source, or may be done on the individual-related. You have noticed that when I mentioned before, you as a person, each one of us in FANAR is at the same time a worker and a member of the public in its normal life, and could be also a patient. So the assessment could be based on the individual-related dose assessment, or could be related to the source. So we consider a nuclear power plant, and we assess what will be the impact in terms of doses towards the population and members of the public. So different types of assessment, which sometimes combine or sometimes they are used only separately, one or the other. Another element in the radiation protection system, a precise formulation of the three principles. We will see those principles more in detail in the next slide. The principles of protection, justification, optimization, and dose limitation. The first principle is called justification because it somehow replies to the question, what is the benefit coming from radiation exposure? If a practice, if the use of radiation source, if a technology implies the use of radiation sources, there must be benefits in doing that. So the first principle says no use of radiation should be done unless there is a clear and net benefit coming from the use of that radiation source. No use of a radiation source or a radiation technique or a technology which involves the use of radiation should be done if there is no benefit, if it is not justified. Now, this may seem to you quite a theoretical principle, but there are several cases and several situations today in the modern world, which is a very complex world, in which the justification is the most difficult and the trickiest part of the radiation protection system. Justification in the medical field. Normally, this is given to the practitioner, to the physician, who has to make a judgment. Will the benefits from the exposure to radiation overcome the risks that exposure to radiation brings along? Or in a different environment, in a security screening environment, I need to, for example, screen participants to a large event to make sure that nobody is bringing in radiation source, and I subject every person to an X-ray. Would that be justified in terms of the benefits? Maybe this time we need to consider benefits to the society, no more benefits to the individual. So the balancing and the assessment becomes more complicated. And these cases are so many. In many societies, the use of nuclear energies is criticized and opposed because some people, some parts of the population consider that the benefits may not overcome the risks. I disagree with this position, but these are topics which are controversial, and as I mentioned before, there are elements in these judgments which are no more objectively available for measurement. They cannot be measured and quantified easily. So justification is the first step in use of radiation, and it's the first principle of radiation protection. The second principle being optimization. This principle is often crystallized into a sentence. Exposure to radiation should be kept as low as reasonably achievable, taking into account economic and societal factors. This means one of the components of the radiation protection system is that any exposure to radiation creates a potential for harm, so any additional exposure should be kept optimized. We should try always to push those towards the lower levels. We always should try to reduce optimizing radiation exposure. But this should be done taking into account also other factors which are not only numerically related to radiation exposure. And the third principle, which is very important, is application of dose limits. Some dose limits should be present, and specifically, we will see later, they relate to detrimental effect due to high dose exposures and stochastic effects due to low dose exposure. Another component in the radiation protection system is a description of the levels of individual doses that require assessment or a protective action. These are called dose limits, but they are also called dose constraints and reference levels. There is a table which clarifies and puts together some of the elements we have already presented before. There are some types of exposure situations on this column: planned exposure, emergency exposure, existing exposure, and some types of occupational exposure, public exposure, medical exposure, as we have discussed. If we look, for example, at occupational exposure, we see that in occupational exposure, both those limits and those constraints exist. Imagine the exposure of workers, which is the case of workers in a nuclear power plant, for example. There are those limits which should never be reached. So an overexposure of a worker above those limits is a situation which requires actions, and it's a situation which is not normal. It should not happen. And in order to avoid that, there are those constraints which represent the effectiveness of the optimization within that specific activity. But in emergency exposure situation, there are no more those limits and those constraints. There are reference levels, which means that there is a guidance on the doses that workers should receive in case of an emergency, but this depends from case to case, and anyway, the concept of dose limit is no more applicable. If you consider, for example, medical exposure of patients, there are no dose limits and dose constraints, although diagnostic reference levels, they relate somehow to those constraints. In the medical field, there are no dose limits because the benefit to the patient should overcome the risks. And it is a physician in the justification, as we said, that has to decide whether that specific technique is a net benefit to the patient or not. So the optimization in the medical field is the application of the so-called approach of diagnostic reference levels, and emergency exposure and existing exposure are not applicable in this case. In the exposure of the general public, for example, there are those limits and those constraints as for workers, and we will see those numerical values later. But in case of emergency or in case of an existing exposure, there are no more limits and constraints, there are only reference levels. So this is the table which presents the elements, what we have called here individual doses that require a protective action or an assessment, and they are a basic element in the radiation protection system. Something which is a bit new in the radiation protection area is a consideration on security and also emergency preparedness. These are new components. Of course, they already existed in the past, but they have been introduced in the radiation protection system since the big accidents in the past and the Chernobyl accident in 1986. A concern for the security of sources is of utmost importance and for preparedness in case of an emergency. I want to discuss now some specific elements which make part of the paradigm, but they are not necessarily one of the topics we have discussed before. The first one is the use of the LNT, the linear no-threshold approach. In the chapter in which we discuss dose and effects, we mention that the current approach in radiological protection is the use of the linear no-threshold relationship in order to express risks at low doses. This is an assumption which has a practical value. It makes radiation protection operationally possible, but this is not a scientific truth written in stone. LNT is an hypothesis which is very controversial, but it is a part of this system today. So we have to remember that the relationship is applied when we are defining coefficients for risks related to doses, and a simple proportionate relationship between increments of dose and increments of risk is an assumption which is scientifically plausible, but it's not scientifically proved. However, regarding this slide, the LNT is a component of the radiation protection system today. Within the radiation protection system, the use of the linear no-threshold hypothesis as a link between the radiation exposure and the additional risk due to radiation is also expressed by the use of nominal risk coefficients. These numbers, they represent the additional risk brought about by the exposure to radiation in low doses. They are nominal because they are the result of calculation, and they are detriment adjusted because this calculation is based on a quantity which is defined as detriment by the ICRP, and it's considering not only the probability, the additional probability of a cancer appearing, but also the shortening of expectancy of life and the worsening of life conditions and so on. So there are several components in this detriment definition. These numbers are important to remember. For workers, it is the nominal risk coefficient is 5.5, 10 to the minus 2 per sievert. So an additional excess risk of 5% per sievert exposure. And for the whole population, which is of course much diversified with respect to workers, it's younger and older and in various conditions, physical conditions, the risk coefficient is different, and namely, it is lower. It is 4.1, 10 to the minus 2 per sievert. Now, these numbers are the result of assessments, and they are reevaluated with time. So these are the latest numbers coming from the recommendation 103, and the previous numbers in the publication 60 were higher. So the revision of the nominal risk coefficient has indeed reduced their value from the assessments made in the 80s, in the 90s, to the numbers which are used today. These numbers are important because they represent the basis for calculating those limits. As we cannot indeed measure the additional risk, what we are using doses in a way to control risk. The Commission has also a specific position on the so-called non-targeted effects. These are those effects which can be generated by radiation in tissues which are not subject to radiation exposure. All these effects appeared since a very long time, and they are recognized since 15-20 years as being something which is not fully understood by the scientific community. For these reasons, today these effects are insufficiently well known to be introduced fully within the radiation protection system. Therefore, we can say that although there is scientific evidence for untargeted effects, they are not today within the radiation protection system. Genetic effects, on the contrary, they were recognized since the very beginning. Since the early studies on the irradiation of the fruit fly in the 50s, which led to the demonstration that genetic risks were indeed possible for radiation exposure. Now, it's always very important to remember, first of all, that genetic risk has been proved in animals and in very simple animals, but it has never been proved in humans. I mean, there was no scientific evidence since the beginning of the studies in radiological protection for transmission of genetic damage to one population from the previous one. So the risk of genetic effects is calculated, but those risks are considered to be very rare. They enter into the radiation protection system via a nominal risk coefficient, which is very small, and indeed its addition to the one for cancer and stochastic risks doesn't change significantly the value of those coefficients. There are some specific effects due to irradiation at high doses, and these were called previously deterministic effects. Today, they are called more appropriately tissue reactions. Now, tissue reactions are those effects which have a real threshold. If the dose threshold is not reached, then they basically don't appear. If the irradiation is above the dose thresholds, then either the frequency or the severity of those effects increases. But at low doses, which is what we are concerned about, these effects, they don't appear, and they should not appear, and they are controlled by one specific set of dose limits, as we will see later. For what concerns other effects of radiation exposure at low doses, risk of non-cancer diseases are indeed recognized, although their quantification is still not very certain. So, in the early 2000s, when the recommendations were prepared, it was not considered appropriate to add other risks than cancer to the irradiation at low doses. Today, in the next revision of the recommendation, most probably those effects will appear because there is more evidence of, for example, cardiovascular effects or dementia, degradation of the brain functions, even at low doses. In the radiation protection system, compliance to the dose limits must be demonstrated by using this approach. This approach says that effective dose should be calculated by one component, which is the component related to external exposure, and should be assessed by using HP, so an operational quantity which is called personal dose equivalent, deep at 10 millimeters, plus a second component which takes into account internal exposure, so intake of radionuclides in the body, and this contribution should be calculated over 50 years. So this is the way for the ICRP, occupational exposure compliance must be demonstrated. Extending this E50, so the committed dose over 50 years, this is also composed of two elements. One is the inhalation, one is the ingestion, and there may be other pathways for radiation intake. Now, if we look into the legislation in the UAE, the legislation is based on the same approach and the same numerical values which are recommended internationally. So it's very important for you to remember that there are dose limits in the Regulation 24 and similar dose limits also for nuclear power plants in Regulation 4, which fix the dose limit for occupational exposure at 20 millisievert per year as an average over a period of 5 years, with a maximum of 500 millisievert in 5 years and 50 millisievert in any 1 year. There are also limits which are fixed for the equivalent doses. For workers, 20 millisievert for the length of the eye, again with the same approach, averaged over defined periods of 5 years, with no single ear exceeding 50 millisievert. And regarding the hands, feet, or the skin, with an average over 1 centimeter square, an annual limit to the dose equivalent of 500 millisievert per year. The equivalent dose limits to the skin apply to the average dose over 1 centimeter square of the most highly irradiated area of the skin. An additional value, a dose limit for the pregnant female worker, has also been defined into the regulation in the UAE, and the dose limit is 1 millisievert for the rest of the pregnancy once the pregnancy is known and has been declared, and this is an equivalent dose to the fetus. Similarly, those limits have been defined also for the general public. The limit for the annual effective dose to a member of the public is 1 millisievert, and this is the same number for the so-called non-exposed workers, workers who are not occupationally exposed as their profession. And there are also those limits related to the length of the eye, which should not exceed 15 millisievert in a year, and or the equivalent dose to any point of the skin 50 millisievert maximum in a year. We have seen what are the basics of the radiation protection system as it has been developed by the ICRP. Now let's have a step back. Let's think, what is the ultimate outcome that we want from a radiation protection system? What is the purpose we want to achieve? Well, the ultimate purpose is to protect people, being workers, being members of the public or the environment. There is a significant effort to develop a radiation protection system also for animals and plants of non-human species in the environment. Now, how do we protect people from radiation? In this paradigm, we try to control risks, and in order to do that, we use quantities which are not risks, but are related to risks, that we have called doses. That's why the whole discipline of radiation protection is about assessing doses, measuring quantities related that can help in order to assess effective dose or equivalent dose, and fixing values that should not be exceeded in the practice. So the control of doses is a way of controlling radiological risks, more or less, and this is the way that the radiation protection system works. In the occupational environment, so for workers, this is subdivided into 3 steps. Those limits related to tissue reactions, those limits related to stochastic effects, and those constraints related to the process of optimization. Tissue reactions, those are very dangerous and they are extreme reactions on the body. They should be completely avoided. They appear only when specific thresholds are exceeded. Those thresholds are exceeded. Never should those thresholds be reached. Specific limits to the extremities, to the lens of the eye, and to the skin are fixed because those are indicators that very high doses are or could be reached. Those limits are expressed in terms of equivalent doses because they relate specifically to those organs, and normally they are the result of external exposure, mainly, if not only. Imagine, for example, an accident. In an accident, a flash of radiation can create a tissue reaction. Normally, this is happening from the outside because there is either a reaction out of control or a machine out of control. It's very rare that intake of radiation within the body is so big to create doses leading to tissue reactions. It can happen, but it's very rare. I can quote the example of Litvinenko some years ago, a spy being killed, being murdered by the use of radiation. Now, the enormous quantities of radiation that Litvinenko was brought to ingest created so important tissue reactions that eventually Litvinenko died due to that exposure. Those are extreme cases. Normally, tissue reactions arise due to external exposure, only or mainly. But we have also another set of limits. These are related to stochastic effects. So if the first set of limits is to avoid tissue reactions, this second set of limits is to keep additional cancer and stochastic risks under a specific risk threshold. These are related to the nominal coefficient exposure risk, or they are related to the linear no threshold theory. They are very important because they define the additional risk to the organism, so they are defined for the whole body, due to exposure to radiation, and they are normally expressed in effective doses. And these are the 20 millisievert or 50 millisievert in a year, which is the effective dose limit for workers in the UAE. That effective dose is indeed the result of internal exposure and external exposure. Now, how should these two be combined? In the paradigm of radiation protection today, those doses are additive. They can be summed, and we have seen an expression, we will see it again later. External exposure can be combined by summing it to internal exposure, and the sum of the two is the effective dose. Of course, as you can imagine, those are two very different exposure situations in which a source is irradiating from the outside or a source, a material, is irradiating from the inside. The hypothesis that these two components can be summed up is one of the hypotheses of the radiation protection system today. This could change in the future. And then we have dose constraints. Those constraints are a set of values which indicate how good or how bad optimization is being done. Because in the radiation protection system we have the linear no threshold theory, so we have the second principle which says we need to optimize radiation exposure and try to keep exposure as low as reasonably achievable, taking into account economic and societal factors. Then the process of optimization is something which is ongoing and needs to be checked. And the good or bad effect of this optimization process is checked against reference values, which are called constraints. Now, these reference values, they are defined for a specific activity or a facility or an environment or one specific practice, and they are subject to change with time. Exceeding a dose constraint is not as exceeding a dose limit. It has a different indication that the optimization process is not fully deployed, that the process is not indeed optimized. They are normally expressed also in effective doses, although they could be expressed also in equivalent doses. Why not? And normally they are the result of external and internal exposure as well. Now it's clear that we could subdivide radiation exposure into these two big chapters, one external exposure and the other internal exposure. This is what we are going to do in the next chapters. We are going to treat them separately and provide you, inspectors at FANAR, with the elements to understand and protect yourself from both kind of exposure. Now, as I mentioned before, the compliance is inherent to this approach that you can sum the two components. The first one, which we are going to treat in its chapter, is the external exposure component, which is normally assessed via the use of an appropriately calibrated dosimeter. That's why it's so important that you wear always your dosimeter. The second component, which is calculated over 50 years, it's the internal exposure component, and this is a bit more complex to understand. If radiation is deposited within the body, it continues to irradiate for a very long time. How do we assess what is the dose due to this deposition? And how is material moving around the body? Is it excreted eventually? Is it deposited in an organ eventually? These are the answers that we want from studies in internal exposure. Now, one last element is the link between what we measure in the practice and the protection quantities, equivalent dose, effective dose. We have said that neither equivalent dose nor effective dose can be measured in the practice. The quantities we can measure, and I indicate them here, kerma, fluence, absorbed dose in specific conditions, can effectively be measured in a specific laboratory for radiation measurements or nuclear measurements. The protection quantities, the absorbed dose to an organ, the equivalent dose, the effective dose, they are used because they are used in the regulation, for example. They are used in dose assessments. They are used prospectively in order to assess the risk before an activity takes place, in order, for example, to measure which way of proceeding is to be preferred. But unfortunately, cannot be measured in the practice. This is where operational quantities come to our help. And this is quite a tricky concept, but it's important for you to understand, because these quantities, the personal dose equivalent, the ambient dose equivalent, the directional dose equivalent, and other, which are defined for internal exposure, they are of practical daily use. So it's important that you understand why they are useful and how they fit into a more general diagram. So we have instruments. We measure the physical world by using instrumentation. These instruments, they are not able to measure the protection quantities. Those protection quantities are assessed by using another set of quantities, which are the operational quantities, and those operational quantities are related directly to the quantities of the instruments. Of course, I'm not explaining this diagram. We will come back again to this diagram when we define the operational quantities. This is just to show you the relationship between protection quantities, operational quantities, and instruments which monitor the physical world. This is the end of this section. In this section, we have presented and reviewed the basics of the radiation protection system as it has been developed by the International Commission on Radiological Protection. This approach is very much shared by most countries in the world, and it is applied with minor differences across several countries, if not all countries in the world. We have understood that a radiation protection system is not only based on science, although its most important information comes from science, from experiments, from epidemiology, and from research, and is the result of a collaborative effort which involved thousands of scientists during more than 100 years. We have understood that not only science is in the radiation protection system, but there are values and there are also some assumptions, which make the system not only a scientific system. There are societal values, there are ethical values, and there are some judgments which have an impact in the way we are doing radiation protection.